We often think of space and time as separate entities, each existing independently of the other. Space is the vast expanse where we move, where galaxies, stars, and planets reside. Time, on the other hand, is what clocks measure, the relentless ticking that marks the passage of moments. We live our lives moving through space, while time marches on, seemingly unaffected by our actions. This duality is ingrained in our understanding of the universe, but this view is an illusion. Albert Einstein, with his groundbreaking theory of relativity, shattered this simplistic notion. He revealed that space and time are not separate, but are deeply intertwined. Einstein showed us that space and time form a single, unified entity known as spacetime. This revolutionary idea changed our understanding of the cosmos. Imagine a piece of fabric stretched taut. This fabric represents spacetime. Just as a fabric can be stretched and distorted, so too can spacetime. Objects in the universe, like planets and stars, rest on this fabric. Their presence causes the fabric to bend and curve. They create dips and curves in spacetime, much like a heavy ball placed on a trampoline creates a depression. These curves are what we experience as gravity. The more massive an object, the greater the curvature it creates in spacetime. Just like a ball rolling on a curved surface, objects in space follow the curves of spacetime. This is why planets orbit stars and why moons orbit planets. This is how gravity guides the motion of planets, stars, and even light itself. Light, though it has no mass, follows the curvature of spacetime created by massive objects. Spacetime is the stage where the cosmic dance unfolds. It is the fabric that holds the universe together, guiding the motion of everything within it, from the smallest particles to the largest galaxies. How can we visualize something as mind-bending as spacetime? It's a concept that combines the three dimensions of space with the fourth dimension of time into a single unified framework. This can be quite challenging to grasp, but physicists have developed a clever tool to help us understand it better. Physicists use a clever tool called a spacetime diagram. Imagine a graph. This graph is not just any ordinary graph, it is a powerful visual representation that helps us map out events in the universe. The horizontal axis represents space. This axis can be thought of as a way to measure distances or positions in space. The vertical axis represents time. This axis allows us to track the progression of events over time. This is the basic setup for understanding the relationship between these two fundamental concepts. By plotting events on this graph, we can see how they unfold in both space and time. Now picture an object moving through space and time. This could be anything from a rocket traveling through the cosmos to a person walking down the street. Its path on the spacetime diagram is called a world line. This line traces the object's journey through both space and time. A stationary object has a straight vertical world line. This means that while time is passing, the object remains in the same position in space. A moving object has a slanted world line. The angle of the slant indicates the speed at which the object is moving through space. The faster the object moves, the more slanted its world line becomes. This shows that as the object's speed increases, it covers more distance in less time. Spacetime diagrams help us understand how different observers perceive events. Depending on their relative motion, observers might see the same event differently. Because motion is relative, what appears simultaneous to one observer might not be simultaneous to another. This is a key aspect of Einstein's theory of relativity. Spacetime diagrams provide a visual language to explore these fascinating relativistic effects. They allow us to delve into the complexities of how time and space interact, offering a clearer understanding of the universe's intricate dance. Einstein's theory of general relativity revolutionized our understanding of gravity. It's not a force acting at a distance, as Newton thought. Instead, gravity is the curvature of spacetime itself. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface. Now, roll a marble across the trampoline. The marble's path will curve as it passes near the bowling ball. This is a simple analogy for how gravity works in spacetime. Massive objects like stars and black holes warp spacetime around them. This warping affects the motion of other objects, causing them to move along curved paths. Gravity is not a pull, but a consequence of curved spacetime. One of the most mind-blowing consequences of relativity is time dilation. Time is not absolute, but relative to the observer's motion and the gravitational field they experience. Imagine two identical clocks. One clock stays on Earth, while the other travels at high speed in a spaceship. According to relativity, the clock on the spaceship will tick slower than the clock on Earth. This isn't a mechanical malfunction. Time itself flows slower in stronger gravitational fields and at higher speeds. The faster the spaceship travels, the slower time passes for it relative to Earth. This effect, while seemingly bizarre, has been experimentally confirmed. Time dilation is a testament to the flexible nature of time in the universe. Time dilation is not the only strange phenomenon predicted by relativity. While time dilation captures our imagination by showing how time can slow down for objects moving at high speeds, there's another equally fascinating effect that relativity predicts. Space itself can also distort. This warping of space is not just a theoretical concept but a real effect that has been observed and measured. This effect is known as length contraction or Lorentz contraction, named after the physicist Hendrik Lorentz. Lorentz's work laid the foundation for understanding how objects behave at speeds close to the speed of light. Imagine a spaceship traveling at high speed past Earth. To the astronauts on board, everything inside the spaceship appears normal. However, an observer on Earth would measure the spaceship to be shorter in the direction of motion compared to its length when at rest. This isn't an illusion but a real physical effect. The spaceship hasn't physically shrunk. From the perspective of the astronauts, the spaceship's dimensions remain unchanged. Instead, space itself has contracted along the direction of motion from the observer's perspective. This contraction is a direct consequence of the principles of relativity. Length contraction, like time dilation, becomes more pronounced as an object approaches the speed of light. At everyday speeds, these effects are negligible, but at relativistic speeds, they become significant. These effects highlight the interconnectedness of space and time, demonstrating that our everyday perceptions of them are only approximations. Relativity shows us that space and time are not separate entities but are intertwined in a complex and fascinating way. Understanding these concepts challenges our intuitive notions of reality and opens up a new way of thinking about the universe. The more we explore, the more we realize how much there is yet to discover. As we continue to push the boundaries of space travel, these relativistic effects will become increasingly important, guiding the design and navigation of future spacecraft. We are three-dimensional beings living in a four-dimensional universe. Our brains are wired to perceive three spatial dimensions, length, width, and height. But spacetime adds a fourth dimension, time. Visualizing four dimensions is incredibly difficult. We can't point in the direction of time like we can with the spatial dimensions. However, we can use analogies and mathematical tools to try to grasp the concept. Think of a movie. Each frame of the movie represents a different moment in time. The entire film reel represents the complete space-time history of the scene. Similarly, our universe can be thought of as a vast four-dimensional space-time continuum. Understanding space-time is not just an abstract pursuit. It has profound implications for our understanding of the universe and our place in it. Space-time tells us that the universe is not static but dynamic. It's constantly evolving and changing under the influence of gravity. From the expansion of the universe to the formation of black holes, space-time is the stage where these cosmic events play out. By studying space-time, we gain a deeper appreciation for the interconnectedness of everything in the universe. We are all part of this grand cosmic fabric, woven together by the threads of space and time. The study of space-time is an ongoing journey of discovery. Scientists are constantly pushing the boundaries of our understanding, exploring the mysteries of black holes, the Big Bang, and the ultimate fate of the universe. The more we learn about space-time, the more we realize how much more there is to discover. It's a journey that takes us to the very edge of human knowledge, challenging our assumptions and expanding our perspectives. So keep exploring, keep questioning, and keep looking up at the stars. The universe is full of wonders waiting to be uncovered, and space-time is the key to unlocking its secrets. Subscribe to our channel for more mind-blowing explorations of the cosmos.